Welcome to SumLab. This is the second video on the nature and behavior of electrons. If you haven't seen the first, the link is in the description. Here's a quick summary. Point 1. Electrons in an atom may be thought of as a kind of wave. This is a more accurate model than thinking of them as little orbiting dots. Point 2. These waves can exist with different modes of vibration at different frequencies and with different wave shapes, and these waves can superimpose on one another in the same physical space. Point 3. The different modes of vibration have different energy levels. Point 4. We can describe the shape of the wave function using four numbers, n, l, m, and s. You could think of these four numbers as coordinates or a street address to describe the position and energy state of the electron. Something else to mention here is that in an atom, no two electrons will have the same n, l, m, and s numbers. No two electrons occupy the same address. So, if you think of a large atom with many electrons, each electron has its own unique set of numbers. This is known as the Pauli exclusion principle. This plays a big role in chemistry because it means that if there is an electron that needs to go somewhere, it must find a space that is vacant. And it can only move to that vacant space if it has the right amount of energy to do so. If it has too much energy, it will need to either get rid of some of the energy or find a different, higher energy home. Now we're in a position to look at how electrons are arranged in an atom and what energy states are possible. And to crack open that, we will need to take a look at what values n, m, l, and s can have. This comes straight from the mathematics, but the model is confirmed by observations of atoms. N can have any value from 1, 2, 3 and upwards. In practice, n does not get higher than 7. We don't get atoms big enough to go up to 8. N tells us about the shell that the electron is in. No atoms are big enough to need 8 shells. L tells us about the subshell that the electron is in. L can have any value from 0 up, but it cannot exceed or equal n. It tops out at n minus 1. So, for example, if n equals 4, then L could be 0, 1, 2, or 3. The subshells are given names, really awkward names for historical reasons that relate to how they were discovered. They're named S, P, D, and F, which stands for sharp, principal, diffuse, and fundamental. I mention this only because it relates to the experiment that we'll do later. In practice, no one ever uses these words, they just refer to S, P, D, F. The one after F has not been named to my knowledge. There theoretically could be a subshell after F, but in practice it never exceeds 3 because atoms only get to a certain size. M tells us about the orbital that the electron is in. The pictures we saw last time give us the shape of the orbitals. M can have any value from negative L up to 0 up to positive L. And S tells us about the spin. S can be either positive a half or negative a half. Let's now construct a table to tell us how many electrons can fit in each shell. For the first shell, n equals 1. L has to be 0, m also has to be 0. This gives us only one possible combination of n, l, and m. So the first shell has only one orbital. 2 electrons can fit in that orbital, one with positive spin, one with negative spin. So the first shell can contain 2 electrons. For the second shell, n equals 2. L could be 0 or 1. If L equals 0, then M equals 0, one orbital containing a maximum of 2 electrons, as we saw before. If L equals 1, then M could be negative 1, 0, or 1. That's 3 orbitals. Each can contain 2 electrons, for a maximum of 6. So the total number of electrons that can be contained in the second shell is 2 plus 6, which is 8. While we're here, I'm going to label the subshells with S, P, D, and F. Well, just S and P so far, because this depends on the value of L. For the third shell, n equals 3. L could be 0, 1, or 2. If L equals 0, then M equals 0, one orbital containing a maximum of 2 electrons. If L equals 1, then M could be negative 1, 0, or positive 1. That's 3 orbitals. Each orbital contains 2 electrons for a maximum of 6. If L equals 2, then M could be negative 2, negative 1, 0, 1, or 2. That's 5 orbitals, for a total of 10 electrons. The total number of electrons in the third shell is 2 plus 6 plus 10, 18. For the fourth shell, n equals 4. L could be 0 or 1 or 2 or 3. If L equals 0, then M equals 0, 1 orbital, and a maximum of 2 electrons as before. If L equals 1, then M equals -1, 0 or 1, 3 orbitals, and a maximum of 6 electrons. If L equals 2, then M equals -2, -1, 0, 1, or 2, 5 orbitals, and a maximum of 10 electrons. Hopefully you're beginning to see the pattern here. If L equals 3, then M could be -3, -2, -1, 0, 1, 2, or 3. That's 7 orbitals and a maximum of 14 electrons. So the maximum number of electrons that can fit in the fourth shell is, add them up, 32 electrons. Whiteboard is running out of space here, so I won't calculate shell 5, but it works out to be 50. And there is a formula for this. The number of electrons that can occupy the nth shell is 2n squared. These numbers that we've just calculated give us the shape of the periodic table. The first shell holds up to 2 electrons. The first row has 2 elements. The second element, helium, has 2 electrons, and so the shell is completely full. The second shell holds up to 8 electrons. The second row of the table has 8 elements. And neon has a contingent of 10 electrons. Both the first and the second shells are completely full. So we position neon under helium that also has full shells. Now, the second shell has 2 electrons capable of going in the S subshell and 6 electrons capable of going in the P subshell. This is reflected in the shape of the table on the second row. 2 elements over here and 6 elements here. This region is called the S block, and over here is the P block. Third shell holds up to 18 electrons, so we expect the third row has 18 elements. And here we have, well, the fourth row has 18 elements. The third has 8, the same as the second. There is some kind of glitch here. Actually, it's not too hard to explain. But while we're here looking at the fourth row, we see 2 elements in the S block, 6 here in the P block, and 10 in the D block, which matches the arrangement of the electrons in S, P, and D subshells. Fourth shell holds 32 electrons, and down near the bottom of the table it is 32 elements wide. 2 in the S block, 6 in the P block, 10 in the D block, and 14 in the F block. The only thing is the F block is usually shoved down the bottom so we can fit it on the piece of paper. Now, let me introduce you to the best periodic table you will ever see. Go to ptable.com. This table has so much information beautifully arranged. It is a great place to browse and discover stuff about the elements. Click on the tab that says Orbitals and have a look around. Over near the center, you see a bunch of little squares. These represent the orbitals. Each one can hold 2 electrons, one of each spin, and these are shown as little up and down arrows. Click on any of these boxes and you'll see the shape of the orbital, and also the N, L, and M numbers. We have seen these before, but these diagrams are nice and clear. Click on any element, and it shows you all of the orbitals that are filled with electrons when the atom is in its lowest energy state, or ground state. And you can also see the electron configuration, which is just a coded statement summarizing how the electrons are arranged. For example, if we click on scandium, we find the first shell, S subshell, holds 2 electrons, 1s2. The second shell, S subshell, holds 2 electrons, 2s2. The second shell, P subshell, holds 6 electrons, 2p6. The third shell, S subshell, holds 2 electrons, 3s2. The third shell, P subshell, holds 6 electrons, 3p6. The fourth shell, S subshell, holds 2 electrons, 4s2. The third shell, D subshell, holds 1 electron, 3d1. The surprise here is the 4s orbital appears in the list before the 3d orbitals. In other words, electrons begin to fill the fourth shell before the third shell was completely full. But we were kind of expecting the electrons to go in the lowest energy spaces first, and the third shell is lower energy than the fourth. Turns out that this is a slight simplification, and this explains the glitch we observed earlier. It just happens that the 3d orbitals are slightly higher energy states than the 4s. and so the order of filling is slightly altered from what we would expect. Now, here is a good exercise, and I encourage you to do this. Click on the elements in order and watch where the electrons go, either by looking at the little boxes or the electron configuration. Here's what you should notice. When you click through the p blocks, say boron to neon, the orbitals are filled with one electron, and then the system goes back to add the second electron with the opposite spin. And when you click through the D block, scandium to zinc, you find much the same pattern, except for chromium and copper. For these, one of the 4s electrons gets promoted, or is it demoted, to the 3d in order for the 3d orbitals to form a nice symmetrical arrangement that turns out to be more stable. One last thing. It would be good if there was some kind of mnemonic to help us determine what order the subshells get filled with electrons. It turns out there is. It's called the Aufbau principle, which is a German word that means order of filling. Here it is. If we list all the shells and subshells in a kind of a table, sort of a triangle shape, then the lowest energy order of filling happens along the diagonals. 1s, then 2s, then 2p and 3s, then 3p and 4s, followed by 3d and 4p and 5s, then 4d, 5p, 6s, followed by 4f, 5d, 6p, 7s. Next is 5f, 6d, 7p, and these are the biggest atoms we have. If this is new to you, then your brain is probably well fooled by now, and you're probably still struggling to see the application of it all. The value of the periodic table is that its shape mirrors the configuration of electrons in atoms, and the way the electrons are configured has a bearing on how the atoms bond together to form compounds. The upshot of this is that elements in the same column or group on the periodic table have similar chemical properties because their electrons are arranged in a similar way. This has been video 2 of 3 on electron properties and behavior, and the hard work is done. Next one, we will perform an experiment and see some of what we've theorized. That's it for now. See you next time in the lab.